It's my pleasure to introduce Valeria Blanco, who will soon join ICMAB as a Ramón researcher. And she did her PhD in Material Science and Engineering in Balseiro Institute in Argentina and worked on hydrogen storage alloys. Then she joined the SRF synchrotron in Grenoble, in particular the ID3531 high energy diffraction beamline. And she was first a postdoctoral researcher there, and then later on she joined the Norwegian University of Science and Technology and TNU, where she had already started working in batteries in Grenoble. Then she continued her work there in Norway, where she became adjunct associate professor, and she was awarded a research project for young talents. And 2 years ago, she joined the Institute of Material Science in Aragon, in Zaragoza, with Maria Zambrano grant for talent attraction of international talents. And then she got awarded the Ramón y Cajal contract, and we are so happy to welcome her from January, we believe, on. Yeah, thank you, Valeria. Thank you for coming. So the floor is.
Yeah, thanks, Rosa, for the introduction. And I will try to speak. Yeah, maybe it's too loud, but. So yes, so I'm Valeria. Thanks for the nice introduction. And the title of this talk is the use of diatom microalgae for anode materials for lithium-ion batteries. So if you see the title of the talk, you see that I'm just combining two things that normally are not that together combined. That is diatom microalgae and batteries. And actually would like to dedicate just a few minutes to what is the motivation of this research topic and why I think it's so important, that why I think we should dedicate effort towards this. And I think it's not working. I think it was working before. Good, yes. So the motivation is sustainability. And as we all know, there is a constant battle that we have as a humankind with the planet, right? That we have, on one side, we have the ecological footprint that is an estimate of how much we need from land, from productive land, just to give us resources and to absorb the waste we produce. And the other side, we have the planet biocapacity, that is how much of these resources can be regenerated and what is the ability of the planet to absorb the waste we produce. And ideally, we would like to have much more biocapacity to sustain much more people than what actually exists on the planet. And that was the situation, but 50 years ago. And since then, we are essentially using much more planet than what we have. And if we put this into numbers and we look what is the ecological footprint and the biocapacity that is normally measured in the global hectares of productive land, country by country, we can see a constant loss of biocapacity throughout the last decades in all of the countries. In some of them, we can see that biocapacity is still super low and we have a huge increase on the ecological footprint. And if we add together all the numbers of biocapacity and ecological footprint of all the countries of the world, then we get the global numbers. And then we can see that there was a time, it was in the early 70s, in which the biocapacity and the ecological footprint just had crossed each other. And since then, we are living in what is called an ecological deficit. So by then, in the early 70s, these concepts of ecological footprint and biocapacity did not exist, of course, and the ecological deficit also did not exist. But world leaders were aware that there was a rhythm at which we were consuming resources that was not good, and that we have to put some stop to the economic growth for the sake of having some resources for the future. And it was in the 72 actually where the aim of, or the seed of the sustainability concept emerged. And this was in one of the United Nations conference. It was the Declaration of Human Environment that is known as the Stockholm Declaration that took place in 1972. And the aim of sustainability actually was introduced in that conference. at that moment, they were saying that we should preserve the natural resources also for the use of future generations. So they introduced this equity criteria between generations, that we cannot just use all just for to fulfill our needs. And it was later on in 1997 that actually the concept of sustainable development was introduced as such. If you see the two definitions that we have, the only difference is that we are changing natural resources by needs. So the core of sustainable development is to be able to meet the needs of the present without compromising the ability of future generations to meet their own needs. But now the needs are not just natural resources. Now the needs are, I would say, aligned into three different pillars. That is economic sustainability, environmental sustainability, and society. And it was just not that long ago, 2015, I guess, where the United Nations declared the sustainability goals, just to put this more like as a concrete thing. So what are actually we are contributing to sustainability? And all of these 17 goals can be linked to each of these pillars. And what we have to consider is that sustainability works as a whole, meaning that if one of these pillars is compromised, then the system or the process is not sustainable at all. So we have to also always consider not only the environment, but how this will affect society and economy. So later on, we now have some targets, specific targets to each of these sustainability goals, and now they are working on the development of indicators. But if you look at this, how this sustainability concept has developed towards the years, we can see that the issue here actually is the ecological footprint, which has not changed at all, almost. And if we break down this ecological footprint into which are the main contributors to this, we can see that the main contributor is carbon. And this is what is called the carbon footprint. And the carbon footprint, actually, what it's telling us is that the world has not enough resources to absorb all of the carbon that we are just building up in the atmosphere. So it cannot be neutralized. So tackling the carbon footprint could be a pathway to diminish the ecological footprint and to have a more sustainable world, I would say. So, and that's why stopping the reliance that we have on the society to the fossil fuel and going to more renewable energy sources is key to tackle not only the climate crisis we are living, but also the sustainability. And in here, batteries come into play because batteries are a great system to store energy that can be produced by renewable resources and to give power demand. So if we look at this spectrum, we can see that lithium-ion batteries have quite good properties in terms of specific power and capacity. And these lithium-ion batteries are right now the leading technology in batteries for portable electronics and also for EVs. But if we consider how much the demand of energy will grow over the years, we know that we will need other battery chemistries. And also we have to think about where are we getting the materials from. And I would say 10 years ago, maybe talking about sustainability when tackling the materials for battery manufacturing was something that was not that relevant. Maybe it was a nice to have option. Okay, performance is good, it cycles well, the capacity is high, and sustainability, well, if it's sustainable, then it's a plus, but it's not that relevant. But in the forthcoming years, sustainability on the battery chain will be more and more important, and new policies are coming. And now we have to start thinking, what is the footprint of the materials we are putting in the battery and also the whole supply chain of the batteries? And actually, this is actually the introduction of my talk. So can we make battery materials sustainable by design? Can we just start thinking about sustainability before going to performance, for example? And I will talk today about the anode side of the battery. You see, we have three main components, I would say, in a battery: the the cathode, the anode material, the electrolyte, which will be the one just delivering the lithium ions from one side to another. We have separators that will just be there to avoid the direct contact between cathode and anode to prevent short circuits. And normally the principle of a lithium-ion battery we have when you plug it to the socket, you charge the battery, lithium ions go from the cathode to the anode through the electrolyte. And when you use the battery just to power your device, the opposite happens, and then we have electrons going in the outer circuit. So in the anode side, currently in most of the commercial lithium-ion batteries, normally the cathode material can change a bit, the chemistry we use, but on the anode side, it's mostly graphite, the material that is widely used. And the reason why we use graphite is because it has a nice storage capacity, and also it has a very nice cycling stability. And this is because lithium interacts with the graphite by an intercalation reaction in the graphite 2D host structure. So when lithium comes in, the graphite expands a bit, and then when lithium comes out, then we have a little contraction. And that contraction is very small, like 8% or so of the volume of graphite, meaning that there are not severe damages or changes in the structure. So it means that the material can preserve its structure upon thousands of cycles. And that's why it's a good material for commercial purposes, because it's stable and we can rely on graphite. But the need of increasing the energy density of the batteries is making graphite to look not that great, because we will need to have much more capacity than what we currently have. And the amount of lithium ions that can be intercalated in graphite is cannot be higher than the theoretical numbers. So we cannot put more lithium in there. So we are actually limited in graphite. We cannot enhance more the capacity. So there are two approaches to tackle this issue. One is just to introduce some higher energy density material to graphite, or just to change the anode material from scratch. So one of the alternative materials to graphite is silicon. So silicon has a capacity, a theoretical capacity that is 10 times higher than graphite. But the intercalation between silicon and lithium ions is totally different, and is via an alloying-de-alloying reaction. So when lithium reacts with the silicon, the lithium will expand quite a lot to form lithium silicide phase. And when the lithium is and the silicon is delithiated, then it will contract. And this expansion and contraction is about 300%, not 8%. And this will actually cause some mechanical instability on the anode, because we'll start with some strain, the appearance of some strain, then crack formation inside the particles, then crack propagation, then pulverization of the material. Then when the material exposes new surface area, then we have new solid electrolyte interface that's being formed there. So it ends up with a huge capacity fade just in a few cycles. So a lot of effort has been put in the last year to try to make silicon work. And some of the strategies that are more successful, I would say, on this are the nanostructuring of the material. Because if we create nanostructures, then we give space for the silicon just to expand on the voids of the nanostructure. And so it should last longer. And also use the use of coatings of the material just to restrain a bit how much it will expand. Another possibilities come from the protocols you use for cycling. You can instead go to the full lithiated state just to stop before it is fully lithiated, so you expand a bit less. And together with silicon, other possibilities or other alternative materials have emerged, and one of it is silica. So silica is quite peculiar, because some years back it was somebody would say, okay, silica is impossible. It's an insulator. You cannot put silica in a battery. And silica actually reacts with lithium ions with a very specific reaction mechanism that is throughout different reactions in which different silicate phases are formed, and lithium oxide plus silicon. And it acts as an in situ convertible oxide, meaning that these reactions will happen once, and then the silicon that is produced there will then reversibly lithiate further cycling. And these phases are supposed to be inactive electrochemically, meaning that the general idea or the general understanding that we have of this system is that silicon will be formed on a matrix of inactive species. So these inactive species can act as a mechanical barrier for the expansion of silicon, because then it doesn't have that much space to expand. And this is the reason why we think this is the reason behind the higher mechanical stability of silica anodes if we compare it with silicon. Of course, this comes at the cost of a lower capacity, but still much higher than graphite. And still, the volume expansion is considerably high. It's not as high as silicon. So even if we try to use silica as anode material, which has many benefits, like for example, we can use silica, naturally occurring silica sources. We don't have to do any chemical treatment on it. We still need to nanostructure the material just to improve the mechanical stability. So if you see, I talk about this, all these buffer phases that will consume lithium at some point. So there is a way that is maybe more like an advanced way of using this principle of having inactive species and active silicon in there. And this is the use of SiOx. So SiOx essentially is like having a composite in which we have at the nanoscale some silicon and some SiO2, some silica, mixed together. So the silicon on the first cycle will lithiate to lithium silicide, and the silica will convert to silicates plus silicon. So if we tailor the oxygen content, how much the silicon to silica ratio, then we might be able to tailor the amount of buffer phases. And then it might be possible to fine-tune the capacity and the stability of the material. Of course, it's in the ideal case, not that as simple as this, but this would be like a more advanced manner to control the formation of these buffer phases and to select how much we want from them. But again, we always have silicon as a byproduct here, and if you have silicon, then we have this expansion. So again, in this case, we need to nanostructure the material. So even if we have super high capacity, moderate capacity, or tunable capacity silicon-based materials, we have to nanostructure the active material. So as I said before, how can we make silicon-based nanostructures in a sustainable manner? And from all the options that we can have out there, there is one that has not been much explored so far, and it's the use of diatom microalgae. So diatoms, I don't know if you have heard of them, but we breathe the air they produce. Actually, 20% of the oxygen they produce, that we have, it comes from diatoms. They are present in every water reservoir, fresh water, marine water, even in land, you will find diatoms in there. And these diatoms, there are like 1,000 of different species, and each species will grow a silica shell, nanoporous silica shell, with a different morphology. So this opens the path. Okay, we can. I mean, it kind of doesn't make sense to try to make a nanostructure at the lab if we have nature making nanostructures already. So the challenge for me is to try to make use of this in a clever way. So we have that the only thing that the diatoms needs to produce these shells is sunlight, CO2, because they are photosynthetic, and water, which can be marine water. It doesn't have to be the water we drink. So the idea is to try to use these materials as an active material for anodes, and to try to change the standard way of making things at the lab for a more sustainable approach. So the vision that I have is to try to think, can we just grow our materials instead of synthesizing it? We'll see. So diatoms have been actually quite, there are lots of research in material science, a lot of publications of people trying to make use of diatoms in different for catalysis, for optics applications, for sensors. But in the battery technology, there is not much actually research. So actually, when I started working on this topic, I had to start a bit from scratch and to think first, where can I get diatoms from? So there are mainly three sources, or this is what I have learned so far. So the first is, okay, normally if you are at the lab, you would like to buy the material just to test it. So commercially available, we can find diatomaceous earth. These are like sediments, deposits of diatomides that were like fossilized throughout the years. And there are millions of tons of these reservoirs, and actually they are being used commercially for water filtration and other purposes. So this is a way you can just purchase from Sigma-Aldrich some diatomaceous earth and see how it works. Another possibility is to go to the ocean and to the harvesting of the diatoms. And this is something that there are companies that are doing this. And I will show you some results of a collaboration we had, because they use diatoms for fish feeding and other, I don't know what else, but fish feeding for sure. And another possibility is to culture the diatoms. So just grow the diatoms that you would like to grow. And then actually there are companies that at an industrial level, they are producing diatoms. Of course, none of these companies, the ones that do the harvesting or cultivation, make use of the shells of the diatoms. They make use of the organics the diatoms produce, because they have some values as the diatoms can produce some lipids, and then they produce pigments or some products that have value from pharmaceutical industries and so on. So they get rid of the skeletons because nobody wants to have a skeleton at home, right? So they just discard them. So when I started this research topic, I started using diatomaceous earth. Maybe it's not the most sustainable one, but at least it's a way to start digging in the topic. So diatomaceous earth, if we look, I mean, depending which is the source we can grab these diatoms from, it will change a bit the kind of morphology that we can get, because actually it's not a single species diatoms growing a single morphology, but rather a mixture of different diatom species that were living at what moment in one place on Earth. So we are just grabbing that. So normally these materials, I mean, you cannot get a very reliable feedstock from that, but it helps just to get an idea of how this works. And also the purity of the silica is not super high. Actually, if you see, we can find actually, for example, iron domains or aluminum oxide domains inside of the frustules of the diatoms. So normally it's a crystalline structure. It was not crystalline when they were living, but throughout the years they will become crystalline, which is good when we do diffraction because then you can follow what's going on with the diatoms. And actually we work a bit trying to homogenize particle size to see what is the effect of the particle when you use this as an anode material. If you see, if the pristine material had a size of around 20 microns, we can download it more to 500 nanometers just to doing some ball milling procedures, which is not easy because actually diatoms are harder than the milling balls. So end up with the situation that diatoms are milling the balls. That's also something we learn about how the mechanical properties of this algae. And if you see, by doing dot milling, we can increase quite a lot the surface area. So that could be a good thing. We also tried some coating treatments to try to improve the electronic conductivity because silica is an insulator, so we have to reduce the electrode resistance. We have to do some coating to the material. And we managed to make a good, nice carbon layers using glucose as a precursor. And then we just made some electrodes out of this, having 50% of this diatomaceous earth, and then carbon black and a binder, and we did the tape casting and used standard materials, standard electrolyte, and so on. The third issue we ran into is that all these reactions I'm talking to you about, that the silicate formation and the silicon and so on, takes weeks to happen. So we had to figure out some activation procedure just to, because we would see like a constant increase in capacity after 500 cycles. So that's not good from a commercial perspective. So we had to develop some what we call electrochemical activation protocols that are just simple steps of doing some lithiation and then keeping the potential at a low value for 2 days just to force the lithium to go inside the material. And then we did the delithiation, and then we kept the potential at high values just to force the lithium to go out from the material. And what you see here are these potential static holding steps. And you see the increasing capacity we got over 5 cycles. And after 5 cycles, the capacity was stable. This is not great. It might be that this material and the silica cannot be used as such as an anode, but this is part of the learning curve that we went through. Once the capacity was reached after these 5 activation cycles, then we can see that we've got the pristine material without any ball milling, just the purchased material into the cell. The capacity was 500 something. If we do the ball milling, we increase the surface area, the capacity is much higher. And if we do the coating, capacity is much stable. And also rate capability improves. This looked okay after 100 cycles. And there is a reason why we didn't publish like what happened above 100 cycles. And it's because after 100 cycles, the capacity starts to decay dramatically. So see, this 100 is like the nice number, and then everything goes wrong. So we try to see why we have this capacity loss after 100 cycles. And doing some investigations in the non-coated material, we can see how the nice smooth surface area of the diatomaceous earth were totally lost. And we can see actually this is typical behavior of silicon. This is typical of this particle disintegration that the silicon has. For the particles that were coated with carbon, we can see that at least the particle morphology, the particle itself was preserved as a whole thing, even though we have a lot of crack formation, islands where the material didn't react so well, and so on. So this is part of it. So at some point, it's silicon that is causing this capacity loss. So then we try to work a bit on trying to improve the solid electrolyte interface to see if we could improve a bit the capacity. That's something you will do with the silicon anodes, but has not been done for the silica one. So basically what as you might know, SCI is quite important for keeping good cycling stability, for having good lithium diffusion path, and also for the mechanical stability of the anode. So a typical thing you can do is to try to optimize electrolyte, salt, and additive. So we didn't take much risk. We just tried to LiPF6, that is the standard one, and LFSI, which is normally works for silicon. And we play a bit with some additives, FEC, BC, and FEC BC, which is normally what industry uses. And then we did the same cycling. And then we can see this is the typical behavior of we had before, LiPF6. With LFSI, we have very similar capacity decrease trend. And we can improve a bit the capacity after 200 cycles if we have some FEC addition to the electrolyte. So we did some XPS at the lab and some HackSPS at the spline beam blind of ESRF to try to see what was this SCI layer made of, what is the chemical composition and the structure layer by layer. And we were able, so then we use same energy for the lab, from a lab source, and we did some etching to try to scratch down a bit and see what was underneath. And then we used 2 high energies, 7 keV and 12 keV, to try to go deep inside of the SCI. So I won't go too much into this, but we were able actually to build some model of we could divide the SCI into 3 different regions. An upper layer would have this poly PC, and middle layer would have more organic and inorganic components, and then the lower layer was where we saw more of the silica lithiation and delithiation, which means that we were able to go through the whole SCI, which is nice, because if you are able to go through all of it, then it means that you can have an idea of how deep it is. Okay, I won't go too much into this, but just to say that there are ways to improve a bit the capacity of the material, even though the material is not super great. So some of the pros of diatomaceous earth is that it is cheap. Capacity that you can achieve is twice that of graphite. Can still improve performance with the optimization of the SCI, but we have a huge high impurity content. The surface area is not so high, so we need to do the ball milling of the material. the properties of the silica, the morphology will change if we change the source. And also we need this activation step that takes 20 days. So we learned something from this, but I don't think we should continue using diatom as a material. So we went to a company that does the harvesting of diatoms in Norway. It's called Planktonics, and we just tried to ask them for some material. It was a collaboration, but there was not money involved here, just an academic collaboration. So most of the first campaign that they did, we got these nice frustules from Blanco species. They look quite nice. If you see, this is a disc kind of algae shell, has different layers, and each layer has a different kind of nanoporosity. So we did essentially the same thing we did with the We do the ball milling of the material. We try, of course, to increase a bit the area. We did the coating with the processes we already have developed for that. And then we did the cycling. Still, we have to do the 5 activation steps, although in this case were not as relevant as before, but still we have to do it. This, I think, is intrinsic to the silica, or at least that's the feeling we have so far. And the capacity starts with the good numbers, but then we have capacity decay over time, again, typical of this silicon issue. But we could have worked more on this material, but the issue was that the following campaign this company did, the material was totally different. So meaning that depending what time of the year they do the harvesting of the diatoms, then you get a different species living there, because diatoms are moving all the time. So just, I would say you cannot use an unreliable, you cannot rely on the material that you cannot propose it for any technology. So we just discarded this option. So we cannot longer use diatoms that are harvesting from the ocean. And this was actually the seed of this project, that is the SUSPAT project, the project I'm currently leading. And for this project, I tried to go to the safe side, and I contacted the company in Sweden that is called the Swedish Algae Factory, and these people just make their living by growing diatoms. And we asked them to grow single diatom species. So the same diatom with the same morphology all the time, and they can grow kilos of these diatoms. So they first grew for us 2 different species so that we could compare differences in how the different morphologies affected the performance and so on. And this is nothing, it's not, it's just an illustration of how a cultivation of diatom is, but it's not similar to what they do at the Swedish Algae Factory, because they grow these diatoms in biofilms. So it's different bodies, but I cannot give a lot of information about the project. So there is this company that is just growing single species diatoms. That is Swedish Algae Factory. And then we have NTNU that is doing the characterization of the diatoms. But now we are not sticking to the silica, because now we want to go to SiOx or silicon, because silica, it's very likely that it won't work unless you do a nice pre-lithiation. It's not impossible, but might not be the safest route. And then we have Sintef, that is also from Norway, that is helping out on the synthesis of SiOx materials. And then we have Uppsala University, which are people that are very experts on XPS, high-space characterization materials, and CSIC, that is INMA, where I come from, that we are more experts also in the characterization of the materials by advanced techniques. So we built a consortium, and now we are working on with the cultured diatoms. So we can ensure the possibility. We will try to do the silica conversion to SiOx, and then we will try the last part of the project to do the graphite SiOx anode. Of course, this is not super simple because we need, I haven't talked about this, actually, this company. This life-size company is led by Emeritus Professor Josh Thomas. It's a startup company in which they are producing helping us to go from the lab scale to the industrial scale. So they will be the ones producing large-scale electrodes. But for that, we need to produce large-scale batches of this SiOx. So I will now walk you through some of the limitations we have at the lab. We want to go big, but then it's not that easy to have good results. So we started with these two species. We call them species A and species B. Species A is a niche species, and species B, I don't remember the name. It was not easy to say it, but there is a publication out of that. You can look at it. So if you see, these are kind of elongated diatoms, and this is a TM image. You can see even from the TM that looks at the frustal is very thin. And if we look at it, if you look at it by SEM, you can see that we have kind of porosity on the side and then a smaller porosity inside. But if you look deeper, you can see actually that the material is not super dense. We have still some internal porosity within the pores. And then we have species B. In species B, the pore structure is more complex because we have, for example, pores inside the pores. So we, in both cases, the composition of the material was quite pure. It was mostly pure silica. And even if you have some impurities, you can control these impurities by controlling the media where diatoms grow. So you can have actually always the same impurity. And if you want to change one impurity by another, you can do so. So we are more like in reproducible conditions in here. So we did the same thing we did with the diatomaceous, and actually we compared the results with it. So in this case, we have an amorphous silica. We did the ball milling with tungsten carbide, the same as we did with the diatomaceous earth. We checked differences in particle size and changes in surface area. But now what we see that this surface gain that we had from the diatomaceous earth, now we don't see a clear gain when we do the milling of the material. Of course, we kind of have to do this just to help of the pack density of the battery. But it's not that you will gain much in terms of surface, and this is due to the morphology of these particles. They are so thin that just cutting it into pieces doesn't give much surface gain. So if you see, particle size distribution is not super different. All diatoms have almost the same kind of distribution in particle size. And regarding surface area, you can gain a bit. You can change some external area from micropore area, but that's all you can get. So this actually is a good thing, because it might be that in the future it won't be necessary just to do the milling of the material. So then we made cells, and then we compared what happened with the material. The first thing that happened is that instead of 5 cycles of activation, we needed 1. And with 1, we still have this capacity gain, but it's not super high as before. And we see this is diatomaceous earth, non-milled material, and this is species A and B. So if this species A has a higher capacity, and also then we have the capacity decay after 100 cycles. That is this is like a magical number that everything starts to go wrong. That, of course, is attributed to silicon. When we do the ball milling of the material, then we don't gain much in capacity, almost all the contrary. And this also is a thing we are facing, that is that particle agglomeration will go smaller in size, and you have other things that are happening there. So not much gain with the change in particle size. But we have some feeling that, okay, we can get better capacity, morphology clearly affects performance. So this is kind of some indication that this could be a good material. So we tested just the bare silica just to compare it with the diatomaceous, but we also asked the company to ship us not just the skeletons of the algae, but the algae with the biomass, because in nature, the algae is growing the biomass, and the biomass is attached to the skeletons. So we asked them just to send us just the diatoms without any major procedure. So they did some simple washing with the DI water just to get rid of some salts, and then they ship us just the diatoms with the biomass. So we did some grinding and drying, some annealing at different temperatures just to try to coat the material with the biomass that was also part of the algae. And then we see the same thing, but doing some acid wash first, just to get rid of impurities that comes with organic matter. And then we did the same thing. grinding and drying, and then annealing. And then we compare the results of how these materials were coated. So if we look at the EDX results, we can see that for the material that was non-washed, we have high amounts of impurities. Potassium may be the most important one, also nitrogen. When we do the acid wash, we just get rid of most of them. And even in the anneal material, the acid wash, we almost have nothing of potassium, but in the non-acid wash, we have quite significant amounts of potassium. We don't know yet still where this potassium is, but it is there. So when we did the annealing at different temperatures for both cases, non-acid wash and acid wash, we saw these are the exact results that, of course, at the beginning, material looks amorphous. But when you start increasing the temperature of annealing, you can see how the impurity peak starts to emerge because they start to become more crystalline. And then we can actually see what are these impurities made of. Calcium oxide mostly. And then we did also TGA on both just to see how much carbon we have in this biomass. Because the amount of carbon is critical to know how thick this coating layer will be. You don't want it to be, if it's too thick, then lithium ions cannot go through the material. If it's too thin, maybe the material is not well covered. So you cannot pick any organic matter content. But at that moment, we didn't have any idea of how much organic matter was there. And it's about 40–50%, which is a lot. Okay, this was not good news. We also did some BET measurements just to see the surface area. We can see there's a huge difference when you coat, when you do the washing procedure. And also we did the cycling. And we were very surprised to see that the non-washed materials behave much better than the washed ones, which means that the impurities are playing some role in the material. Might be that they are affecting conductivity, or it's not very clear for us, but we didn't expect to have better behavior of this. But still, the amount of carbon is too much. So actually what now we are working on is we ask the company, when they produce the algae and they deliver to us the silica skeleton, they do two treatments. First, they get rid of most of the organic matter by some mechanical treatment, and they use some acids to burn the remaining organic matter. So now what they are doing is they prepare some samples for us without doing this second step. So maybe we can get, instead of 50% of organic matter, maybe 10%. And then maybe that will change the whole thing. But we'll see. If the results are good, maybe I won't comment on them too much, but still this is something we are trying to explore a bit to see. That also will make the process more sustainable, and also we gain a bit by getting rid of most of the organic matter. So the pros of this is that we have reproducibility, we have higher silica content, surface area is high, we don't need to do ball milling to increase it. We can select the silica morphology by selecting the diatom species, and we can scale this up because this is already happening in an industry. So the material is already being produced with high reproducibility at an industrial scale. So now we want to go to SiOx. And there are two ways to go to SiOx. Normally, any silicon-based material in the industry is made by what is called the carbothermal reduction. And the carbothermal reduction is actually a process that is done in an arc melt furnace at high temperature, like 2000 degrees. You just mix the silica with could be wood chips or any coke or any carbon precursor, and then you get the reduced material with carbon monoxide that will rapidly convert to carbon dioxide just by temperature. So we have some intrinsic carbon footprint. That is because we are using carbon here. And then you have the other carbon footprint that comes from the electricity we used, and we made use of carbon for that. So we're trying to go from another reduction that is a magnesiothermic reduction reaction. So in this route, we use magnesium as a precursor, and we can reduce the silica to silicon or SiOx at temperatures that are much lower than these 2000 degrees. And this is super important because we want to preserve the morphology of the diatoms. That's why we use the nanostructured material as a feedstock. So if we cannot then keep the morphology, then it won't make any sense. So the idea is to try to play with this reaction, to try to preserve the morphology, and also to try to go for a zero carbon footprint synthesis of the material. Of course, it's not as simple as a one reaction, because normally this will be the reaction that should be taking place. But normally you get a lot of extra reaction products like magnesium silicide, magnesium silicates. And this, there is not much research into this, but it is believed that this reaction is so exothermic that it will trigger other reactions to happen at different particle places. Some of them will happen more at the interface, some more in the material, and so on. So we have to be super careful when we do the synthesis of the material. The most, this phase, magnesium silicide, of course, if you have magnesium silicide, you reduce the silicon yield, but you can wash it out when you wash out the magnesium oxide with simple hydrochloric acid. The real problem is if you have magnesium silicate, because for magnesium silicate, you need HF to remove it. And the issue it's not only that you have to use HF, which nobody wants to use that, of course, but HF also reacts with silica. So if you want to try synthesize SiOx, which will have silicon and silica, and then you have silicates, and you have to use HF, then forget about the silica. You will get only silicon. So what we try to do is to play a bit with the stoichiometry of the reaction to try to go to a situation in which we will have silicon-rich SiOx, and then more like a silica-rich SiOx to see what happens. So we just mix all the components together. We add sodium chloride because we want to go to more large scale for this. And then if the reaction is so exothermic, we will need an agent to buffer the temperature changes. And sodium chloride is great because the melting point is 800 degrees. So it means that if there is an excess of heat, then sodium chloride will melt and everything should be okay. So we use a lot of sodium chloride on this, and then we did some reductions at different scales, from milligrams, 2 grams. We are trying to go to 100 grams, but then all of this is a mess. So this is a species A, as I told before. This is from EELS, actually, some idea of the thickness of the frustal. These have just a few nanometers thick. And we try to do first in the bar material, the SiO2, this SiOx reduction. So these are the first results. If you see, this is 1:1, 1:1.5. No, sorry, this is 1:1, but with different sodium chloride contents. So if you don't add any of the sodium chloride and you just do the reduction, thinking that everything will go well, then you find that particle morphology is totally lost, meaning that there is some heat that is being building up in the reactor and just affects the morphology of the particles. So we had to add more sodium chloride to keep the material morphology. So once we fixed the sodium chloride content, we went to, this is just some electrochemical results. You can see the 1:1, that is when we lost the morphology, the capacity was higher, but it's decaying along with cycle, and in the other ones, capacity is lower, but more stable. So then we fixed sodium chloride content and did the reduction for different ratios between silica and magnesium to have SiOx with different oxygen contents. And this is what we got. So this will be the case when you have a more silica-rich. This is the bump of the silica, amorphous silica. And this is the situation we have more like silicon-rich SiOx. So if you look at this, you will see that in the first two cases, particle morphology is preserved. We can see actually these are silicon crystals are being grown at the surface of the silica. But when we go to the 1:2, so have more reactions or more heat is produced, then these small silicon crystals starts to grow a lot, and then they just collapse, the nanostructure collapses, and then we have huge silicon crystals in there. So this means that we have to be more careful with fine-tune more the amount of sodium chloride when we increase the amount of magnesium on the sample. So we did some cycling also. We did the same 50% of SiOx with the carbon black and some binder. And you can see that the capacity for the silicon-rich is higher, but it decreases a lot with time. When we went to the 1:1.5 content, it's lower and still has some decay. But when we have the 1:1 ratio, then it's not super high, but it's super stable. And for a commercialization perspective, this is important to consider. Okay, it's not super high, but at least it is stable. So now we want to gain more control on magnetothermic reduction conditions, because we have a lot of byproducts formation. We don't know the issue is the heat. The issue is we are changing also the stoichiometry of the reaction. So we did a lot of, check the time, okay, I have to finish, I will go fast through this. So we went to the synchrotron and we planned a bunch of experiments, not just one in situ, but 9 in situ experiments. So we will try to see what is the effect of using diatomaceous earth or the niche species as a reagent. We will try to see what is the effect for each one of these to use a different ratio, 1:1, 1:1.5, 1:2 between silica and magnesium. We will also try to see the effect of the heating ramp, how much that affects the formation of the byproducts. So we went to BM01 of ESRF. They have a very nice setup for this kind of experiment. You can do fast heating, you can heat up very fast actually. And we put the material inside the sapphire capillary and did a lot of tests to see what happened. This has to be, of course, loaded inside of a glove box because the magnetothermic reduction happens in an argon atmosphere. So I will go very quickly through this. So this is wave 1 to 2, silica to magnesium. This is by the diatomaceous earth. This is for the Nistia. We can see actually this is the heating ramp. This is from readable analysis, some reconstructions. So we can see actually that magnesium, one of the key findings is that at the beginning the reaction proceeds through a solid state, solid-solid regime. And this solid-solid regime, before magnesium actually evaporates, happens more when the material is amorphous and thin. So this means that magnetothermic reduction could be maybe a solid-solid process if the material is good enough. But if the material is too thick or too crystalline, then you need magnesium to evaporate just to be able to go inside of the particles and react with it. Also, something we saw was the formation of this magnesium silicide phase as an intermediate phase that then will just go away. But in our case, we have it as a reaction product, which was very strange because it should not be. So then we also changed the ratio, and we saw that if we change the ratio, we start seeing magnesium silicate. So we also try to play a bit to try to promote these reactions to happen, to see why we have these materials. And we see if the reaction is at 650, going here, then you would not have this magnesium silicate. And we were at the synchrotron, we were at about 800 degrees. We didn't see the magnesium silicate, so we say, just let's heat it a bit more to see if it reacts, and we have this reaction product, and we heat it more, and then we have it. Meaning that if we have magnesium silicate, it means that the temperature inside the reactor is much higher than what we think, and that we can control the formation of this phase just by lowering somehow the temperature of the reactor. These are good news because it means that we can have some practical guidelines of how to do this. So then we also changed the rate, and we can see actually that if the rate is very slow, the magnesium silicide that is intermediate will become a reaction product. And if the heating ramp is very fast, then just it will be an intermediate. And what we think is that the reason for that is that this magnesium silicide that is being created, if you see also here the amount is much higher than when we heat faster, that this magnesium silicide that is being formed as an intermediate this layer starts to become thicker, and then difficults also the magnesium for further reaction with the silica. And so, but if everything goes faster, then the magnesium silicide phase will be more like thin, and then you can have more reaction proceeding. So this is just a submitted manuscript, but these are the general ideas. What happens when you use a crystalline or an amorphous material with different morphology? What happens if you change the ratio of reactants and so on? So, summary. I went fast. So, we think we can use these exoskeletons of diatoms as a sustainable and reliable source for silicon-based materials. We can get reproducible properties of the materials if we do single species diatom culturing. That is not easy, but it's possible and it's already being done industrially. This doesn't work. So if you grow single species diatoms, then we can pick the morphology we want. We tested 2 species, but there are thousands of them. So you could grow your own diatom and see what happens. And then that we can produce SiOx, although now not in a very reliable way when do upscaling. So a few milligrams, we can have a tailored oxygen content, but then it's not that easy, but we are working on this to produce SiOx from diatoms through magnesium thermic reduction. And some of the ongoing work is to try to see the on-pot synthesis of SiOx carbon using this biomass that is in diatoms and trying to do the magnesium thermic reduction and the annealing from the biomass to this carbon layer just in one pot synthesis. We will have to explore pre-lithiation because when you have these inactive phases, the silicates, you need to do some pre-lithiation. And now we are moving to graphite SiOx. We have some results, but I cannot show you much about this, but yeah, looks pretty nice. Yeah, and that's all. So yeah, thanks to Zaragoza University, the Eranet project, and then there's all the partners that have participated. Life Size, Uppsala, CSIC, NTNU, and the Switch at the factory, and Sintef. Yeah, that was
Valeria. Question from the audience. I will put the microphone because otherwise people online wouldn't hear.
Yes, thank you very much. I have several questions, but I'll just make the main. But first of all, I like the work and the presentation. It's great. It's a kind of sustainability within batteries. It's great, and I think you will succeed. But I have some doubts about the magnesium.
Yeah.
Okay? Of course, carbon is like iron is made. That's always been made like that. Why? Because it produces CO2. So that is ruled out in this century. Yeah. But magnesium is not made with the production of CO2, but it's an energy-intensive material.
Yes.
And I don't know, I wonder about the techno-economic analysis.
Yeah. So actually, we were contacted by a company. If it was a Spanish one, but I don't remember from where, that they were interested in the magnesium oxide, that is a byproduct of the reaction. But the issue that we have was if we could make use of the magnesium oxide, and that would have some relevance from the economic, for another industry. But the issue that we have so far is how to separate, because now we wash out the magnesium oxide with hydrochloric acid. But if we could manage just to separate the reaction product, then we could give that another value, and that would open the path to some co-utilization of byproducts. But yes, I know about magnesium. I not say it's great to reduce the carbon footprint, but on the other side, has some cost. Yes.
Renewable energy, but it would be energy intensive.
Yes.
So I wonder about other reduction methods.
Yes.
But let me ask you about what you call the kind of pre-treatment of the silicon oxide electrode.
Yeah.
This activation process that you mentioned in the beginning is electrochemical.
Yes.
Okay, so there you are reducing to some extent.
Yes.
Okay.
But we are reducing all of the silica to silicates and silicon, so you have no control on the formation of the buffer phases.
Yeah.
But
maybe that way there might be a direct reduction.
Yeah, I mean, we're working a lot. Actually, we have a PhD thesis now that is finishing, trying to control this electrochemical reduction to see if we can actually select which reaction pathway the silica will go through to increase the capacity. But it's super challenging.
Very much.
Yes, super challenging.
That's why I'm making this comment. But I feel that there should be a way to reduce.
I agree.
I mean, you have made a great work in studying the magnesium mechanisms, but maybe you need a better, to start with, a better reduction process.
I totally agree. Yes.
Yeah.
I totally agree.
You mentioned sodium chloride, you know that electrochemical reduction in water is not the same as in molten salts. And
yes.
I don't know, there might be some room for improvement.
Yeah, I agree. Yes.
But congratulations.
Okay,
it's
thanks.
very ambitious, very nice.
Yeah, thanks.
everything now, you wouldn't have worked for the Ramonica house.
Yeah, that's true.
So you need room for it. Structure to make both of them. Just on the line, why didn't you try just with the one poster? I think there is it's in the plan, but
We did it, but we didn't work. I mean, we had a master thesis we started with that option because it was better, but we, instead of going to SiOx and carbon, we formed silicon carbide. So, and we did some studies trying to understand why we have silicon carbide instead of what we want to have. And so we did other kind of coatings. First with the different amount of glucose to try to build a good, to have more carbon on the material, and then to do the reduction. And we learned that the issue is that we have so much carbon that the magnesium cannot go through. But it might be that this another option we are exploring now, that that the company will deliver to us material with reduced amount of organic matter. I think in that case it would totally work, because if we could reduce the organic matter amount, then it should work. It works with when you have glucose, for example.
because this growth path gives you a lot of options.
Yes.
The starting material that
Yes.
process, and it would be basically probably more sustainable than all the process.
Yes, that's what we aim for. Yes.
From the side of the energy, the carbon footprint, the chemicals that you have to use.
Yeah.
About HF,
Yeah, but yes, but it's just that you know, when you are in the project, is a dynamic thing. So we came up with this idea of asking the company not to get rid of all, because we were in a situation that either we have 50% of organic matter or nothing, and we thought that there was nothing in the middle. But now we have the chance to have maybe 10% or 20%. So I think that could actually be the pathway to.
maybe in the atmosphere, if you have some oxygen, you
Yes.
get rid of
Yes. Yeah. Yes.
Actually, I had a lot of trouble to get carbonization and to have it really oxygen free, and to have to deal with carbonizing, for example, cellulose is nightmare because you remain with a yield of almost nothing.
Yeah.
And maybe if you have little bit
Yes.
of air inside, even controlling the humidity and stuff.
Yes. I think I need more students. But yes, I agree. Yes.
Have you considered using the silicon monoxide gas?
Yes, we have.
You haven't done it.
We haven't done it yet, but it's that's something that we're discussing now in the consortium. Yes.
Yeah, because seeing that is in a consortium, I think they know a lot
Yes.
about it. They produce silicon carbide,
Yes, exactly.
and it's a very complex. Well, they make it in Atkinson furnaces, which is
Yes.
yeah. Very pollutes a lot.
Yes.
It's a current technology, and
Yes.
in there are a lot of reactions taking place, and silicon monoxide is one of the things that appears.
Yeah, we're exploring that at the moment. Yes, with SINTEF. Yes, yeah.
Thank you very much. I really like the approach. Really, I guess I felt that
Yes. So now yes. So as I said, this company only can grow like 5 different species. Actually, I didn't tell you about, but we have a lot of issues as well, because at some point they also have contamination between species. It's not super straightforward as I'm selling this. But I'm having a collaboration with the BMCC, that is the Basque Microalgae Carter Collection, and they have 700 of different diatom species, and we are working on growing like to select them. But the thing is, morphology is also not morphology of the different diatom species are not that reported, I would say. So people use them just to produce lipids or chemicals, but they have not looked at the skeletons. So there is a little, we are trying now with different morphologies to see if that plays a role, but they are struggling a bit to get enough amount of materials because for the company it's easy, but for a lab just to produce large scale of grams of material is, but yes, we are trying to explore that, yes. 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 Yes, yes, yes. Yes. It's very clear, yes. Not there is a link. It's really, yes, indeed a link, yeah.
Well, concerning the morphology, I wonder, you mentioned the grinding and non-grinding, but maybe the whole structure, not the whole structure, you need to grind that to some extent, but not so much that you lose the hierarchical nature of
exactly, just to keep the pores. Yeah.
Fractal porosity here,
Exactly.
and maybe have the perfect room for silicon particles to expand without breaking. So maybe that's another comment along the line of specific
yeah, I totally agree.
species
yes.
with an ideally suited porosity.
I totally agree. So the thing is now the current approach for using diatoms in batteries, if you see that there's not much on this topic, it's just to pick any diatom that is out there. Use it. It's what we did also when we started until we figured out that we're not going anywhere. But I think we have to do a lot more on the characterization to see different species, different morphologies, to see which one is more suitable. Actually, if you look at the literature in silicon, there is not a preferred morphology. People say, yes, you need to nanostructure, but there is no consensus of which nanostructure do you want to have. We don't know.
But let me ask you a second part of the question. Is the data you have in the not ground samples, you do have lower capacity, we saw that. And maybe longer cyclability?
Yes.
Voila.
Yeah. Yes.
That is the proof that is, well, the proof.
Yeah, that is improved.
Is proving that the expansion is being limited by that. So you yourself said, who cares if the capacity is somewhat slower if I can make 1,000 cycles instead of, I mean, it depends how much your vocation of this work is application or publishing. This application, please take it into account the techno-economic analysis, consider these kind of things, and cyclability.
I guess actually in the future, maybe we could sacrifice a bit performance for the sake of sustainability, or we will have to, but we'll see if that's the case.
Thank you. I don't know if there is anybody online to ask a question, so we could solve the one mute because I'm not seeing the chat already.
Pardon, there's one.
Okay.
This person said that they will ask privately.
Okay.
So there's nothing more.
Waiting for that. Okay. So I don't know if there is any burning question. Otherwise, maybe it's time for lunch. But actually, you have one.
Well, I can ask just a general question about an introduction to speak about sustainability and how the carbon footprint decrease. So if you could do like a carbon footprint analysis of the different components. How much would be the decrease of carbon footprint by introducing this certain amount of silicon?
We're working on that. Actually, as diatoms, just they use CO2 to grow. So we have some hope that it will have be a low carbon footprint. We have some issues now with, companies normally they don't want to disclose a lot of procedures they use. So we are working on that. At the end of the project, we'll have a life cycle assessment of this. Some numbers may be that we will just, but not super accurate. But yes, we will. The idea is to have some numbers just to prove that this actually helps, because that's the purpose of the whole research. But yes, we have to start doing life cycle assessment, I think, in everything we do. Yes. Yes.
Okay, so thanks very much, Valeria, for the nice
Okay,
talk and
thanks.
the discussion. So thank you very much.